weather and climatic changes, atmospheric pollution and disturbances of the ozone layer, worldwide magnetic storms that disrupt radar and radio, telephone communications, and even cause power failures. All these may well be controlled by eruptions on the sun, which affect Earth's magnetism and create the auroras by means of a vast engine around the Earth, the magnetosphere. Because this magnetosphere can affect Earth in so many ways, understanding how it works might help us cope with climate and pollution variations, and even help us in planning the use of our food and energy resources. But how can we start to understand the magnetosphere? In 1600, William Gilbert told us the Earth was a great magnet extending into space. 10 years later, Galileo Galilei turned his telescope on the sun and recorded how its surface constantly changed. But then for 300 years, the sun and Earth pursued their courses, and no convincing theory was able to connect Galileo's solar changes with Gilbert's terrestrial magnetism. Until a solar theory in 1890 suggested that the sun throws out particles which travel to the Earth to be caught by its magnetism. In the 1950s, the sun's own magnetism, it was suggested, flowed into space to envelop the Earth and generate the auroras high in the terrestrial sky. Yet this was only speculation on how the sun might affect the Earth through an invisible magnetosphere. Only by actually getting measurements in space could the true facts be unearthed. In the late 20s, Goddard, the American, built the first practical rocket craft. The Russian Sputnik was the first space success.
2, 1, 0.
The American Explorer soon followed, carrying with it a Geiger counter. The signals produced by the counter enabled Dr. James Van Allen to confirm that he was recording something real but unexpected in space.
It repeatedly did the same thing in the same general range of altitude and latitude and longitude, and therefore it must be a true physical effect that we were observing.
This was the first discovery in space. The Van Allen radiation belts, particles invisible to the eye, which came perhaps from the sun, were trapped in the space around the Earth by the planet's magnetism. This was the first step in establishing a link between the sun and Earth through the magnetosphere.
And when the radiation belts were discovered, I was very keen on the idea that the fast particles from the sun would be able to fill these radiation belts, and that the stored particles we were seeing there were in part, or perhaps in major part, coming from the sun. And so the paper in which the word magnetosphere was coined was that there would be a region around the Earth where the Earth's magnetic field dominated the circumstances.
The first concept of the magnetosphere was that of a region where Earth held particles that were captured from the sun. But did these particles really come from the sun? To find out, instruments had to be fired further out into space to really discover if the erupting surface of the sun did throw out particles and magnetism all the way to the Earth. And from space, this answer came back. Streams of particles flowed from the sun, dragging out the sun's magnetism, a solar wind rushing into space. But Earth's magnetism in the magnetosphere deflected the solar wind around the Earth. So how then could the solar particles get in and be caught? Solving this space problem could be difficult.
You're going to have them penetrate to the atmosphere. And so one of the exciting things that have been done in the last few years was find that if we went clear above the Earth's poles, that plasma from the sun would directly come down into the atmosphere.
This was the breakthrough. Solar particles detected entering directly into the magnetosphere. While within the magnetosphere, further measurement showed what was also invisible to the eye. Seas of plasma particles around the Earth, and huge particle streams moving thousands of miles back from the tail, perhaps to directly ignite the brightest auroras. But what could drive the magnetosphere into these vast movements? Could the solar wind rushing past outside the magnetosphere supply the energy?
Well, if I knew the answer to the question of how energy was transferred from the solar wind to the magnetosphere, I wouldn't be sitting in front of this camera talking about it. I'd be in my office writing as hard and as fast as I could to demonstrate what I believe to the colleagues which are also investigating this problem. It is contentious.
One theory hinges on a magnetic connection. Magnetism from the sun connecting with and dragging back Earth's magnetism. This would work like a dynamo in space, transferring energy into the magnetosphere, where it is stored until suddenly released in a magnetic storm to disturb the Earth and create auroras. For such auroras appear to be created when stored energy is released in a violent eruption throughout the magnetosphere. But where can proof of this be found? One place is the Arctic, where auroras are seen almost every night. And scientists search for clues to show how the magnetosphere collects energy from the sun, stores it, and suddenly releases it to the Earth, creating auroras in a burst of energy equal to that of a large earthquake. So analysis today concentrates on finding how the magnetosphere works and, in particular, what triggers its energy releases. Could it be changes in the solar wind?
The solar wind does not flow steadily and regularly. It carries perturbations, shock waves. Even the magnetic field changes in direction and intensity. When this happens, an instability is triggered in which suddenly an explosion occurs in the tail, in which magnetic energy that has been accumulated during a certain time is suddenly converted into particle energy. And that typical solar wind particle that had been trapped in the tail now suddenly is accelerated toward the Earth.
So, changes on the sun, which change the solar wind, appear to trigger an energy-filled magnetosphere into a sudden spasm, creating a magnetic storm, the brightest auroras, and affecting the whole Earth environment.
But there are still many of the apparent effects of the aurora borealis and the magnetic storms that defy detailed explanation. So there's a great deal more to be learned in the ionosphere and in the upper atmosphere of the Earth.
So investigations continue. This is a computer simulation of the Earth and auroras from space, part of an experiment to measure exactly how magnetosphere energy creates them. And beyond this, there are active experiments.
You really want to try to actively perturb the magnetosphere, the ionosphere, and the atmospheric system in controlled ways so that you're actually doing a laboratory experiment. You know what the input is, and you can measure the response of the system. And when we get to that point, we'll be able to really probe the specific processes which couple these regions together.
In Canada, there is an active experiment underway in which radio signals, which disturb the magnetosphere, are received from the opposite hemisphere of the world, the Antarctic. The signals injected here arc through the magnetosphere to give a record of the changes that are happening there. The most active experiments will be done with man in space, on the space shuttle.
With the space shuttle, we get the opportunity to put man into the experiments. Given the new capability that the shuttle will have, we'll be able to
we'll be able to conduct a brand new variety of experiments that we've never had the capability to do before. And the scientist will be able to interact with the medium surrounding the vehicle, will be able to probe the medium, perturb the medium, and measure the responses. And that's really the way you understand things.
So what is understood of Earthspace today? Laboratory simulations of a magnetic Earth and the solar wind streaming at it have been able to produce a visible representation of the magnetosphere. But the picture is blurred and out of scale. Only space measurements are valid in constructing a true diagram of the magnetosphere and its movements. Simplified images of this complex engine in Earthspace, where until recently there was thought to be only empty stillness. This is, however, a gauge of our present-day understanding and ability to predict how changes on the sun will, in some ways, affect the magnetosphere and Earth environment. So today, at forecast centers like this, the sun is kept under watch around the clock.
Activity in region 331.
What kind of activity you have?
The filament in 331 is active. It is shifting off band to the red. Flare. Beginning in 331. Start time 1958. Location north 13, east 28.
Dad, I've got a big flare. Could you give me some help?
Today, we know that the magnetosphere is a complex engine through which the sun causes enormous disturbances to the Earth's environment.
FAA, this is the Forecast Center in Boulder. I'd like to report a major solar flare in progress.
When we learn all the details of how the magnetosphere works, we will be able to predict its effects on the atmosphere and its influence on short and long-term weather patterns and on changes in the Earth's ozone layer. Then we would know what changes to expect in our environment when we see the sun shaken by a huge eruption. All this lies in the future, but many think the groundwork is now being laid.
In region 331? Well, that's right. You probably will have some effects in a day or two.
East 28.
Oh, this is a big one. It's still on the increase.
Still rising.
There are some effects of magnetic storms that are controversial. The apparent effects on the weather. We find some fairly convincing evidence that if there is a very large magnetic storm, that there are worldwide effects at the jet stream level of the atmosphere, with low pressure centers that correspond to major storms over the Gulf of Alaska deepening in the first 2 or 3 or 4 days. But of course we know that the storms are associated with dumping of electrified particles from the magnetosphere into the Earth's atmosphere. We then take a look at what happens to the winds and to the temperatures of the atmosphere at about 35,000 feet above our heads. There seems to be no doubting the fact that there is a weather effect.
Beyond climatic changes, there is the effect on living organisms when the whole magnetosphere is disturbed during reversals of the Earth's magnetic polarity.
Now, at present, the magnetosphere exerts a vital shielding influence on the surface of the Earth. But during magnetic polarity reversals, the magnetosphere, for all practical purposes, disappears. That shielding is removed. A major solar flare occurring during a reversal in polarity of the magnetic field would produce ozone depletions of a large enough magnitude that it would almost certainly have serious effects on the biosphere, if you like, on living organisms on the surface of the Earth. I don't think this is a mechanism that we have to worry about too much. Although we are due for a polarity reversal in terms of the geologic past, the polarity has been stable now for nearly 1 million years, and that, from the past record, is about as long as it ever is stable.
So this is our world. Around it, Earthspace, the magnetosphere system through which the sun affects so much of our environment. A better understanding of Earthspace is a key to maintaining the harmony of our planet's future.